Okay, so we have a little group called Falcon Space, and this sort of melded into APEC over time. And Jeremy Reyes, Todd DeCiato, and Jeremiah, and also Sean, who's joining us here just on audio, are all part of that group. And I'm going to show you a little presentation, just a whole bunch of pictures, giving a bit of a timeline of how we got to where we are and what exactly it is we did. So starting off, we have, let's see, can you see that now?
Yeah, I see a picture.
Okay, so this is me and Jeremy. He came down to the lab in February of 2019, and Jeremy, of course, alien scientist, he went on a road trip down to Virginia to the to some library in order to do some research on antigravity. And I hit him up on the way back, said, "Why don't you stop by the lab, check this out?" This led to a live stream tour of our first warp drive laboratory. This was back in March. Not much was learned over here. We were talking about T-Towns and Brown and stuff, but in the comments to this video, which I can't access right now for a moment, for some reason, was the first time I had any inkling on this experiment called Alzofon, or Frederick E. Alzofon put out a paper in 1981 called Antigravity with Present Technology Implementation Theoretical Foundation. It was published in the Joint Propulsion Conference in Colorado Springs, Colorado. And this is a paper that is fundamental to the work we're doing. Todd DeCiato's theory is very similar to this. And I've heard several other theories that sort of connect with the same fundamental experiment that he outlines here in the paper, which I'll show you in a moment. It's basically, again, a laminar magnetic field or homogeneous magnetic field around a sample of aluminum with a little bit of iron added to it. It's important that the aluminum be of very high purity. The iron is added as a stepping stone to sort of build up what's called dynamic nuclear orientation, which happens in the nucleus of the atom where you're orienting the subatomic particles. Todd is trying a similar thing, and Todd, correct me if I'm wrong on this, with nuclear magnetic resonance, where he's hitting the Larmor precession of the entire nucleus, versus what we're doing over here is hitting the Larmor precession of the valence electron. The valence electron is the same for every material, so it's 28.025 gigahertz per Tesla. So no matter what material you stick in there, you are going to be hitting the valence electron if you get the numbers right. And accuracy is key over here. You need like 1 part per million in order to hit these frequencies correctly. 28 gigahertz, that's 28 billion cycles per second. So if you're not accurate to like at least 1 millionth, you're not going to, you can be hitting it wrong and weakening the Larmor precession. So it's very important to get everything correct in this experiment. So the first thing I purchased was this signal generator, found it on eBay for a steal. It's capable of 9 to 9.5 gigahertz, which is the frequency range that Frederick Alzofon was using when he tried this experiment. When he tried it in 1994 in the basement of a big university where they had an EPR machine. And apparently they got weight loss of 80% in a 1 gram sample within less than a second of turning the device on. So this was, very exciting experiment. So I decided to go forward with it. We got the signal generator. Wasn't sure what to do next. There's the back of the signal generator. Interesting thing about it, it is serial number 110. So that probably means it's the 10th one that was ever built. Never found another one of these since. It also has, I don't know if you can see over here, there's the capability of changing the pulse output, which is important because you don't want continuous RF controlling the electron spins. You want to pulse it every like 5 milliseconds or so, so that then the orientation of the electron, which is then energized up, can move into the core. And the iron is in there to help transfer the orientation to the aluminum, and the aluminum is there because it acts as a reservoir of dynamic nuclear orientation. This is how I understood it from David Alzofon, who wrote a book on it. David is one of Frederick's two sons, and they both kind of are very into this science. And David wrote 2 books on the subject, and Daniel Alzofon was working with Hathaway and some other lab. He was also working with Hal Puthoff and some other physicists related to NASA, and they've seen some very strange effects with this experiment. So I really wanted to move forward with it. So what we did was we went to AlienCon. This is me and Jeremy at AlienCon, and we presented over there in one of the booths, showing off all different types of anti-gravity. We met a couple very interesting people, including this guy, Carl Miller, who is an RF expert, and he agreed to help us out. He donated some equipment and sent it directly to the lab. This is a RF antenna for that range. It's the X band of microwaves, so it's 8.2 to 12.4 gigahertz, and we're smack in the center of that with 9 to 9.5 gigahertz. There's the other side of it. You can see that is the entire antenna, because gigahertz are really small frequencies. I think the wavelength is somewhere around like that long. You're talking about like 2 inches or so. He also gave us this nice cone, or the waveguide, and some wire as well. And we also got this for making the material, the aluminum iron mixture. Picked this up also on eBay. As you can see, it has 5 nines on it, so it's 99.9999% pure aluminum slugs, and we melted that along with a little bit of iron, and we ended up with these little samples. And this is the force sensor that we used. Jeremy actually recommended that. There's very few scale measurements that graph on a computer that are available online. They're very difficult to find too. So this was a great find. As you can see, it's not shielded in this picture, and we later discovered that that was a major problem, because RF does interfere with the crystal inside that is essentially using the piezoelectric effect to give you a voltage. And so we had to shield the hell out of this thing. And in fact, several layers of shielding went on it at the end in order to get a clean signal. This is the test rig, and here is the electromagnet that we started building. A lot of work went into this electromagnet, and this is the first iteration of it. It's not connected at all. Everything was loose. And then I took it to a local mechanic, and we were welding it together. And yeah, I set this up. Here's the original setups. The red bucket over here is full of salt water, because we're worried about just the extra RF in the room, giving us biological damage and whatever. So I filled the bucket full of salt water to act as a load for the microwaves. This is pick this up also off of eBay. Great deal. Goes up to 22 gigahertz. It's a spectrum analyzer. And it show you the the waveforms and pulses and everything. It's a really great piece of equipment that we picked up. That's my 2-year-old. He figured out how to turn it on. Oh, next came the well, we needed some sort of amplifier, because the signal generator is putting out milliwatts, and we quickly realized that the most of the stuff being sold on eBay, the traveling wave tube amplifiers, are broken. Tubes are broken. So I bought one, it was broken, ended up returning it. And then I found another one that was pretty cheap, and the guy didn't even have a way of testing it. And he offered a full refund if it doesn't work. So he sent it over, and sure enough, it didn't work. But here's the exciting part. It didn't even turn on properly. And for an electrical engineer, when something doesn't turn on, that it's usually an easy fix, because it could be a fuse, it could be a transistor, it could be something simple. Turns out the problem was in the low voltage side that powered the tube. It wasn't in the tube itself, which is pretty much the entire device. And the most expensive component of this device is the tube. So I was able to fix that by the help of the manual that came with it. and it started working. And you can see it right over here, and that is the traveling wave tube amplifier. It puts out 20 watts. I had it set up with the scale over here, and there was a multiplication device, like a leverage arm with the sample in there. Here we can show you, this was after several hours of experimenting. I found that there was a certain spot where I was getting around 18 or 17% weight loss. Just show you this briefly. It's around a 30-second video. Let's go back to 892. You can see the weight loss over here on the laptop. And I'm changing the frequencies very slightly. Yeah. The fans you hear are from the cooling of the tube. And here I'm turning on the, what was that, the attenuator. That's basically shut off the power and put it back down to 0. And we can see some sort of weight loss was happening in the sample. Again, this is close to the noise field, so we really wanted to take it to the next level. But we did see some promising results with this experiment, so we wanted to move forward. This is kind of what we really need. This is a proper EPR setup, or you can use this for NMR as well. And I actually found one used out in California that we're looking at picking up. These things weigh a ton, or several tons actually. So the magnet we have right now has a cross section of homogeneous field that is probably around 1 inch and 1 inch by ½ inch. We need something a little bit bigger to get a larger sample in there. Also, something that was brought up by Tanya, who's here as well, is that having a horn antenna like we had in that setup and bombarding it from the side is really wasting most of your potential RF energy. And you know, it's not going into the sample. You're getting, you know, less than 1% going into your sample. So what you really need is a tuned cavity, like meaning it's all encapsulated. You have holes for you know, string to hold it up to measure any weight loss. And that's something that we're moving on to next. The tuned cavity needs very accurate, you need to be able to move the parts in and out so that you know when it's tuned, and you need a reverse power meter to know when it's tuned, but that is all in the next iteration of the experiment. So what happened next was we were going to make some samples. These are, we decided if we're going to do dynamic nuclear orientation, let's just try a whole bunch of samples. You mentioned, David mentioned earlier, Linton Moulton Howe's sample that had bismuth, magnesium, and I think it was tin or something like that, layered. So we have over here the bismuth, magnesium. We did it with iron as well, because according to the theory, iron acts as a catalyst to bring the dynamic nuclear orientation to other materials that aren't so ferro. And we are encapsulating them inside of epoxy. These are all the different iterations that we made, different mixtures of iron, aluminum, niobium, bismuth, bismuth trioxide, vanadium, copper, nickel, silver, tin, and magnesium. And we did 28 different samples. Jeremiah came down to the lab. He was helping me with Falcon Hybrid, which is the hybrid battery business. And at night, we were working on the anti-gravity stuff. These are all the samples. We made them in little tin cups, and little cups, and we put them inside a vacuum chamber to remove all of the bubbles, get nice, clean samples. And we started setting up. You can see over here, Jeremiah's working with the setup. This is an isolator, what he has in his right hand. Isolator is like a one-way valve, like a diode in RF. This is the attenuator, and this is the horn antenna. And again, we're just putting the setup together. We also realized the magnet and the welding was a really bad idea, so we had to take that apart. And the next thing we did was try to smooth out the top of the the center iron cores. And we didn't really have much tools in the shop at that time, and we got a little creative. This is Jeremiah's idea. Let me show you exactly what we did.
Bet y'all never thought Alzofon would look like this. We ended up rounding out the core pieces because the field laminarity was an issue. And they're looking good now.
Okay, yep. So that was how we did that. And we finally had an entire test setup. This was like cutting it close. He was about to fly back the next night, the next morning, actually, and we were up late working on it. You can see over here, we got rid of that huge cone because it was dispersing the energy way too much. We want to concentrate the energy as much as possible. So I found this other cone on eBay and stuck it on. It's supposed to work for the X-band frequency. And here's the setup from the other side. You can see this is a Yagi antenna that's also for the same range, and it's attached to the spectrum analyzer over here, so we can see what's actually coming out the other side, make sure the pulses are correct. And this is the sample holder. This is the first iteration of the sample holder. It didn't work very well. We moved on to something better. There's some other angles of it. These are all these samples. This is the newer version of that sample holder. Went with a just 2 strings on the side that were held down by weights, and this was 3D printed. And this was the newer version of the holder. So the electromagnet would go over here. We would have the scale measurement sliding along this top bar, and this bar over here is connected with some bearings and a little brass rod, giving it a very free range of motion. This experiment also yielded some results. It was, again, it was in the noise range, but we did see something there enough to get excited, but not enough to publish. Here's the AutoCAD for the new device. I actually made it a little larger so it would fit larger samples. And here is the sample holder. This was one of the first versions of the sample holder, using little pieces of clay to tension the wires or these are actually fishing line that we're using, that allows us to move up and down. There was hysteresis problems because there is a little bit of iron inside the sample. We're talking around like less than 1% of the sample does have a little bit of iron. And these samples, by the way, are inside of epoxy. So there's tiny pieces of aluminum and tiny pieces of iron that are all mixed together. We didn't have the, what do you call it, that shaking device to the vibrator, the ultrasonic vibrator yet in order to disperse them properly, but it came out however it came out. And again, we did see something, but it was within the noise floor, so it's hard to say exactly what it is we saw. And here's a problem, it's out of alignment. We had to fix that. Okay, so this is the next time Jeremiah came around, we decided to get a little bit more professional. We found out that next door there is a humongous lathe that they do not know how to use, and they were more than willing to lend it to us or let us use it. The thing is bolted down to the floor. It's freaking humongous. And we straightened out the core pieces. This was happening during Estes Park, and we would run out during the breaks and work on the electromagnet over here. You can see we also made new bobbins for the electromagnet, added a bit more copper onto it, and we got this Gauss meter over here from a local company because our Gauss meter broke. Everything was done sort of last minute. This was Ubered over from South Jersey. Turns out it had an analog scale on it that didn't work for us very well because we couldn't read it properly, and we had to return that. And here we are playing with the checking the homogeneity of the field, which is like the difference between the center and the outside. You want to make sure that there's same amount of magnetic flux or magnetic strength throughout. Okay, and this is the new setup with the new electromagnet. This is the power supply. We had to modify the power supply as well, changing out the pots to give us more resolution on the current, because the current is all that really matters. We added in a capacitor as well so that the signal or the load for the power supply would be a little bit more steady. And here's a close-up of the setup. This knob over here would control the frequency. This would show you where the frequency is at. This will show you whatever. This will show you basically how much current is going into it. But we realized that there wasn't enough digits on the current to really show you exactly, how steady this power supply was. So we added another shunt in, like custom-made shunt, and connected it up with this Fluke voltmeter, and that was down in the millivolts, and it showed us that the power supply was putting out a pretty steady power, and that is extremely important. There's it from another angle. So what happened next is, with this setup, we started to get headaches. 20 watts of RF X band gives you a headache, and that was not comfortable at all. So we decided to finish building our Faraday cage, and Jeremy's over here putting in the floor for the Faraday cage. We have an 8-foot grounding rod in the center, and that's how we sprawled out the wire. I think it's like a 1/4 inch or 1/8 inch, I think around 1/4 inch plates, aluminum plates on the floor, and it's a bilayer Faraday cage with a basically capacitive layer. There's wood in between, and there's aluminum on the inside, aluminum on the outside, and they're both connected to separate grounding rods. This is inside the Faraday cage after we started setting it up, and we were shielding the wires as well because we were getting noise problems. And this is a thermal image. We have a couple thermal images coming up showing what was heating up in the sample. We expected the coils, of course, to heat up. They heat up very little because when we added more copper to the electromagnet, the total wattage to achieve the magnetic field, which was around 3,300 Gauss, that was necessary to have our more precession of the valence electron at 9.5 gigahertz. It dropped down to only like 15 watts, so there wasn't much energy being used to power the electromagnet, which was that was good. There was a little bit of temperature rise in the sample, which indicates that we were getting something, but it was nowhere near the 20 watts that we were outputting. There was probably around 1 watt that was entering the sample at most. It was around 46 degrees centigrade. You can see there at the hottest point. That was the point where the RF was directly hitting the sample. Isolator had a little bit of heat. We also used the heat sensor to find where there was kinks in the wire and possibly RF feedback, and we had to take the wire apart to fix that. So infrared camera is something that's definitely useful. This was a new waveguide that I designed on a 3D printer, and we covered it with aluminum tape on the inside. That is to concentrate the energy more directly into the sample. Over here, we had a bilayer of aluminum that was protecting the scale from the RF energy. And then there's several layers of shielding on the scale because the scale kept on interacting with the RF in this chamber because RF is bouncing all over the place in here. And again, there's a bucket of salt water over here to try to absorb most of it. Had some really interesting wave patterns when we turn this thing on. Move anything ever so slightly, like 1/10 of a degree, and everything changes. So it's like super, super sensitive with this setup. And you can see it from another angle. Jeremy named this the EPR NMR laminar spintronic alignment rig. That was our electromagnet. We still have this set up inside the Faraday cage. Okay, this is the equipment. We had an oscilloscope hooked up to the signal generator so we can see the pulse waves, pulse of on and off, and it's supposed to be at 5 milliseconds. So we had to hook that up to confirm that as well. And this was the final setup. Again, we have the shunt resistor over here to read our current. Current now is way down. It's around 3 amps and 4 amps and 4 volts at around like 15, 16 watts total. And we were measuring our millivolts over here as well. And we got the paper. This is a spy cam, so we're able to see if anything was moving inside the chamber, from a camera coming in and it's all going in through the wall over here. There's these holes in the wall where we're able to stick all of our probes and our power into the chamber. We did see some results here as well. We got really excited one night when we saw like 50% weight loss, but that turned out to be noise from RF. Then we had to shield it even better. But again, there is a possibility that what Alzofon saw over there was noise from his microwave setup. So that's something to look into. This was about the limit of what we can do with the 20-watt system without going to the chamber idea that Tanya talked about. Next thing that happened was Jeremy Riss was searching on Craigslist, and he found this lab that was going out of business. And he started sending me pictures of all the shit they had over there for sale. And he sent a picture of this. It was a 5,000 volt power supply at 0.5 amp. And I don't know if any of you know this, but to find a power supply like this is pretty darn hard. I've never seen one before. And right away, what I thought was, get that piece. We need it. We're going to use it for power a klystron. So they gave it to him at below scrap value. I think he paid like $50 for it. The thing weighs like 200 pounds. It's fucking awesome. He brought it down here to the lab, and sure enough, it was broken. So we had to fix that as well. It was actually the safety features. There's tons of like safety devices on here, so we had to remove all that shit and just make it run direct off this big variable, turn thing. It looks almost like a safe.
There was like mice nesting in it, and there was a whole bunch of that was just terrible, man. It was everything in that shop was covered in mouse urine and mouse crap, and like we had to clean the whole thing out. It was pretty bad. But
yeah, we cleaned it up, man. We reversed the rectifier direction, and so we could have the inverted output polarity correct. The klystron needs a floating high voltage negative cathode, so it was not configured for that exact application. But hey, it does jack out almost 2.5 kilowatts at peak, so not bad.
Yeah, this thing is a beast. It actually running it here in the second lab, which is far away from our input power for the building. We were blowing fuses when we were powering this thing up, so it really is a beast. It takes a lot of energy, and it's something that can power a klystron. And there were tons of klystrons on eBay, so we picked one up. This one was around $300. It goes up to 3,500 watts, which is more than our power supply can supply. So whatever, we got it. It's in the C band. And interestingly enough, when Jeremy went down to that lab to pick this power supply up, they also had a whole bunch of C band waveguides that were all tuned to a very specific frequency. And these waveguides were tuned. I showed it to Tanya. She was like, "Oh my God, I feel bad for whoever tuned those things, because they were literally tuned to 6.281, way down. It had like 5 digits of the tune frequency that can go into it, meaning that any frequency above or below will be pulled out." So that was a very interesting find as well. And we were able to hook it up all together and get a very accurate microwave output. And now this of course means that we're only going to be able to control one side of the experiment, meaning the magnetic field will be able to change, but the RF is not going to be able to change. We're going to have the RF steady. And since it's a correlation between electromagnetic field or homogeneous electromagnetic field and RF hitting it at the Lamar precession of the electron, valence electron, therefore that means we're going to need a very accurate power supply, DC power supply, to run the electromagnet. These are the components. This is a channel selector. We didn't end up using this. Here's it from several different angles. It looks pretty small. It is pretty small. This thing weighs almost 100 pounds, and it has extremely powerful magnetic fields. We can't get anything close to it. It'll pull, like, when we were attaching parts to the output over here, it kept them pulling wrenches in. It has very powerful magnetic fields. This over here was some aftermarket construction that we did because the wires were getting frayed, so we put on some Teflon and we put on some Kapton tape and then covered it all with high temperature silicon in order to protect the device. And as Jeremiah just mentioned, the power supply was putting out a positive output, and these need electron flow, so they really needed a negative output. So we had to change the polarization of the rectifiers in order to get a negative output from the power supply. This is what it's rated for, 8.3 kilovolts DC at 1.07 amps. So we're talking like 8,500 watts is supposed to be going into this thing to run it at peak power. That's a crazy amount of energy. Okay, here's some more pictures, and these are all the channels that are available. Oh, this is a great book on dynamic nuclear orientation that was recommended by David Alzofon. I picked that up as well. This is a waveguide handbook that I picked up on Amazon, and it is stock full of all these crazy long mathematics and stuff that I couldn't make heads or tails of. And when I was speaking to Tanya, who is our waveguide specialist, she said that most people don't understand all this stuff and just do everything off of experimentation, because there's so many variables and there's so many different components that go into waveguide engineering that it's really above anybody's head to comprehend. It's kind of stuff that's done on a computer. You
can solve the Helmholtz equation for that chamber, but theoretically, but does it really help you if you're off by a little bit? And you need to tune these things, and they really require like an art and finesse in the experimental sense.
Exactly. There's really no way around actually just doing it, because you can calculate the math to hell, and then there's a tenth of a millimeter difference inside your chamber, and all that's out out the window. So everything needs to really be done manually. And what she recommended was to have a setup where you can move the panels in and out with screws, and then you would have a piece of what was it? A piece of carbon, like graphite inside, and you just run the chamber for a little bit and check it with an infrared camera, and then you'll be able to see where the waves hit it and where it got hot, and then you'd know whether you're in tune or not. You also need a reverse, forward and reverse power meter in order to know what's going on. None of this stuff is sold commercially. It's not. It's all stuff that you have to pretty much figure out on the fly. This piece over here is the forward and reverse power meter, but it needs to be hooked up to these little guys over here, which are power meters in their own right. They're cross guides, so they're reading the magnetic component of the wave, and because they're offset, they can read the magnetic moment at different the magnetic component at different intervals along the tube. And we were able to see some numbers over here. I'm not really sure what they correlated to or how much power is actually coming out. This is a double isolating system that is meant for the C-band, and that goes into an input antenna that then went to a massive, what do you call it? It went into a massive attenuator that was rated for like 50 watts or something like that, into our signal analyzer. The last thing we want to do is blow up our signal analyzer. It can only accept 1 watt. That thing could put out several hundred or several thousand. So this is the rough setup that we had going on here. We also needed power for the tube itself. And the power needs to all be floating, because it's at a potential of 35 or 5,000 volts DC, negative DC. So you need to have a system to both power the coil, which is at 6.3 volts at, I don't know, like 10 amps or something like that. And of course, that was done with an RC battery, like a little lithium battery, and it's floating on a piece of PVC to shield it. And we have 2 buck converters that provided the power for the tube. And we can see this from a couple different angles. Here's Jeremy and Jeremiah at the lab. I've got the Alternative Propulsion Engineering Conference sign just above my head right now. And Yeah, here's the whole setup. Oh, also, I plan on using these capacitors over here. These are 10,000 volt capacitors. We're going to put them all in parallel. That's how they're wired up right over here. And we're going to attach them to the output of the power supply. And what that's going to do is when there's pulse, when we're running the final experiment after we get all the tuned waveguides set up, this will give us a little extra power because we'll be able to pulse it. It's going to drain the voltage and go back and forth, and we'll be able to get a little bit more than 2,500 watts available from this power supply, and bump it up a little bit. Pinky was inspecting it, and let's see what else we have here. Yeah, this is a side view of the entire experiment. Oh, okay. Yeah, so then here's the power supply. So this is basically the entire experiment. Over here, you can see it actually running. This is not the experiment. This is just testing the components because we're missing some components. And this experiment, by far, is one of the hardest experiments we've ever tried. If we were ever to, get successful results, none of these components would be used in an actual craft. We'd have a coil around the entire perimeter of the craft, which would create a homogeneous field line in the shape of a flying saucer, which kind of like makes sense why they are shaped like flying saucers, because that is where the homogeneous field lines are. And then we'd probably radiate the microwaves from the outside or inside the skin of the craft somehow. There's many different ways to do this. Another idea that we've looked at was the ARV, or the Alien Reproduction Vehicle. This was brought up by Mark McCandlish. There's a lot of speculation about it, whether it's a real thing or not, but this was shown to Frederick Alzofon, the inventor of this experiment. And he looked at it for a second. He said, okay, what's probably going on here is this is another way to create dynamic nuclear orientation. What's happening is the coil on the outside, this red coil over here, is being pulsed by these massive capacitors in the base, and alongside with the aluminum flywheel spinning, it creates dynamic nuclear orientation, which is contagious, by the way. It's not just like, we're not just making the flywheel weightless. We're making everything that surrounds it weightless as well. Think of it like electromagnetism. You have a magnet, and it magnetizes everything that's around it. What this is more like nuclear magnetism, where you're orienting the core of the atom, and that effect is also contagious. It also goes to everything that surrounds it, and therefore there's some other propulsion device in the craft that allows it to fly. So this whole thing is all about inertial mass cancellation or gravity shielding. Two different ways of looking at it. It's possibly either inertial mass cancellation or gravity shielding. Both of them are not really mutually exclusive, because you could run the experiment and see weight loss and say, oh, it's gravity shielding, or you could say it's inertial mass cancellation, but there is no experiment that can really differentiate between the two because of the gravity mass equivalence. So there's just two different ways of looking at the same experiment. And I've actually been contacted by lots of people about this experiment with all different theories about why it would work. It seems like everyone wants to throw in their hat on the theory side of why this experiment would work. But Todd DeCiato and Wayne Ojala, who has a channel on YouTube called Fail Forward Research, definitely check him out, are the only people I know of, other than Hathaway, who's no longer working on this, who are actively working on these experiments. And we all communicate continuously, night and day, about the latest progress and what it is we're working on. So we called this experiment, Wayne came up with the name Easy Alzofon, because it's a much easier way to do it. And here's a picture of that craft, or something similar to it, that was pictured by some pilot. So it's possible there was really a craft like this. Now, so for Easy Alzofon, we need a aluminum disc spinning. So I went down to the Metalworks shop here in New Jersey, and we picked up some aluminum. And when choosing the aluminum, they asked me, what grade do you want? So I was like, okay, what's available? And started scrolling through it. And there was this one aluminum called 5052 aluminum. And if you check online, it has, I think it was like 96, 97% aluminum. And then there's magnesium, and then there's iron. And magnesium and aluminum have very similar properties in terms of acting as a reservoir for dynamic nuclear orientation, per Frederick Alzofon. So they can be used interchangeably. And the iron is needed as well to act as the catalyst to bring the dynamic nuclear orientation into the core of the magnesium or aluminum. It's also interesting that it's called 50-52 because it's missing area, 51. So I thought that was kind of cute. We picked this up. They were balanced as well, and I'm here in their metal shop making sure that it was balanced properly, and it sure was. We spun it up to very high speed. Next thing we did was make a coil for this experiment. Here it is. I used that as a bobbin. Didn't work that great. I mean, the wires are a bit of a mess, and it was a lot of work. And I've determined that in the future, if I'm making any more coils, it's a two-man job at the minimum, because you can't really do this on your own. You need somebody to hold the wire. You need somebody to do that. It's a lot of work to make these coils properly. There's some more pictures. That's the spool of 300 pounds of wire that we have here in the lab. And so we unspooled it. And there's all the disc sizes. I promised Todd one of these if he wants to try the easy Alzofon version of it. And here is the setup. It's actually right behind me if anyone wants to see it. We did try it 2 weeks ago with just a DC field on the magnet. There was some results, but it might have been air current, so I wouldn't say anything is positive. But we then wanted to try with the pulsed magnetic field. And Jeremiah recommended we use the high voltage capacitors, which I have over here as well, right behind me, to pulse the magnetic field inside the coil. And when I set that up, the high voltage was jumping in between the coil wires, meaning that it wasn't actually making it all the way through the coil. It was shorting to itself. Sparks were going everywhere. There was breakdown of the insulation. And now the picture's not in order. We pretty much determined that the proper way to do it would look something more like this, where the wires are encapsulated in a very strong dielectric. In this case, they claim they used glass. We're thinking of using epoxy because that's what we have available. And epoxy and glass have similar dielectric parameters. And in order to do that properly, we need to get a proper bobbin. We need a separator. Jeremiah recommended we use fiberglass in between each layer of coil. And we need a vacuum chamber that can then suck out all of the air bubbles. So that meant we needed to get a larger vacuum chamber. And I'm just going to bring the laptop around over here. And I'm going to stop the screen share so you can all see what it is I'm talking about. Okay. So we got this vacuum chamber over here. It's quite a bit bigger. And it will be large enough, hopefully, to build this coil. This is the fiberglass. And we're just waiting on the bobbin materials that are coming in. It's a big PVC pipe. We're going to have to put some separators on either side of it in order to build this coil. It's going to be like a 2- or 3-man job. And once we get that going, we'll be able to take the experiment to the next level. Over here, we have the capacitors I was telling you about earlier. These are the ones that we were using for the pulsed version. We also have 2 rectifier tubes that we're using for isolation, because we're going to be pumping energy into the capacitors via our high voltage power supply, but we don't want the, when it goes into the sinusoidal phase, when it goes to positive, because it's a negative output. When it goes into positive, we don't want that feeding back into our power supply and blowing it up. So that was kind of important that we have isolation there as well. We also threw in a row of resistors. And this is the current setup we have over here. I'm not going to run it right now, but that's how far we got with the Alzofon experiment. Any questions?